In this lecture, we will study what is the condition for the maximum power to be transferred to the load. We learned previously for DC networks that the maximum power is delivered to the load if we make the load resistance equal to the Thevenin resistance. However, now we will extend this for AC circuits and find out what is the condition and how the power transferred to the load is maximum given a Thevenin equivalent circuit is given to us. So let's say we have a network with an AC voltage source, and let's say this is a Thevenin voltage already calculated, an AC voltage. You have a Thevenin impedance and a load connected to it with a load voltage VL, the AC voltage VL, and the current IL flowing through it. So given this Thevenin equivalent circuit, we need to find out what is the impedance value, ZL, which will make the power transferred to this load as maximum. All right. So before that, we know that power delivered to the load can be written in terms of its load resistor and load current as this equation. So what is IL and VL for this network? The IL, the AC current, can be written in terms of Thevenin voltage divided by equivalent impedances, ZL. And the voltage across the load can be written as the voltage divider rule as ZL over ZL, impedance of the load, plus the Thevenin equivalent. So what is the impedances here? Z Thevenin, so this circuit has would have a R Thevenin plus its reactance, the imaginary part. And similarly, ZL is nothing but RL plus the reactive part of the load. So what is going to be the sum of the ZL and Z Thevenin? We will calculate as nothing but R Thevenin plus RL plus the imaginary part XL plus X of Thevenin. Right? So these are the two equations of current and voltage across the load. So we put this ZL plus Z Thevenin in equation 1 and 2 to find out what is the current and voltage flowing through this network. So we put this value, put in 1 and 2, insert these values in the current, which will turn out to be V Thevenin over. So what we are going to put is that we are actually putting the amplitude of this in this one, right? So how we do the amplitude for this one, because we are writing here the amplitude of the current. So amplitude of the current for this part is nothing but square root of the x component, which is this x component. This is x and this is y component. This is the x squared. This is nothing but x, and this is nothing but y. So this is going to be x squared plus y squared. So R Thevenin plus RL squared plus x Thevenin plus XL squared root. So this is nothing but the amplitude of the current. Amplitude. And similarly, the amplitude of the voltage can be written as, using the voltage divider rule, V Thevenin here,
We put this in equation number 2. And ZL, so ZL in equation number 2 can also be written as the amplitude of RL square plus XL square, RL square plus XL square under root divided by, again, R Thevenin plus RL square plus X Thevenin square impedance square sorry, this is the whole square under root. Right, so again, this is the amplitude. This is x squared plus y squares. Let me erase this and this. Okay, so now we can finally substitute in the power formula. So we have this power formula, the first one. This is your power. When we substitute the current value in this power, we will find out substitute IL in power equation. We find the power delivered to the load as half V open circuits or V open circuit or V Thevenin square RL divided by R Thevenin RL square plus the imaginary part, reactive part. So when is the power maximized? In the AC circuit, so we need to remember that in the AC circuit, the power delivered to the load is maximized when the impedance of the load is equal to the complex conjugate of the Thevenin equivalent. So instead of unlike the DC circuit, when the RL becomes equal to R Thevenin, you deliver the maximum power. In this case, the impedance of the load when becomes equal to the complex conjugate of the Thevenin impedance, then you deliver the maximum power to the load. And how did this term comes in? You can also derive this term by setting, doing the derivative for this one or this one, and you can actually reach to this term, right? So the maximum power can also be written as, so this is ZL. What is the complex conjugate? What is ZL? So Z complex conjugate for Z Thevenin can be written as R Thevenin minus, so complex conjugate means the J sign is reversed, X Thevenin, which is equal to RL plus JXL, right? So when we put this condition for the maximum power in the above equation here, when we substitute in equation number 3, the maximum power can be written as half V Thevenin square or V open circuit square. RL will be replaced by R Thevenin divided by, so this R Thevenin, RL are equal, right? So R Thevenin plus R Thevenin square plus, so this part, the second part is going to cancel out because X Thevenin XL is minus JXL now, right? So this is nothing but X Thevenin minus JX Thevenin. So this is cancel out and this will be nothing but VM V Thevenin square R Thevenin divided by R Thevenin plus R Thevenin square, which is nothing but 2R Thevenin squared. And this can be also written as 1/8 V Thevenin square R divided by R Thevenin. Right? So this is how, this is the condition when the power delivered to the load is going to be maximum. we can also represent this on a phasor diagram. If this is your RL, this is your XL on the imaginary part, then ZL is going to be here, right? And the angle theta Z is going, which is the load angle, is going to be this one, which is actually nothing but subtraction of the voltage minus the current delivered to the load. So VL minus the IL. So this is how we can find out the maximum power to the load. So let's do an example. Let's find out how in a circuit whose values are given to us, how we can find out the impedance of the load for delivering the maximum power transfer. So let me draw this circuit. This is our current source. This is Z1, which is equals to 2 ohms. We have an inductor. Whose value is J1. A resistor whose value is 4 ohms. And a load ZL. We don't know the value of this load. We need to find out. The value for this current source is 4 of angle 0. Right? All right, so what we have to do is that we have to find ZL, impedance for the load, for maximum power to be transferred. So for finding V Thevenin or R Thevenin, let me change the color. What we do is that we actually remove the load. Right? So we remove load first to find out what is the, from this point will be the V Thevenin or R Thevenin or Z Thevenin in this case. So in this case, it's going to be Z Thevenin impedance. So let's label the currents. Let's call it I. Let's call this I1, and the current flowing through this one is I2, and these are AC currents. So we'll label it like this notation. What is going to be now the V Thevenin? So V Thevenin or V open circuit at looking from these 2 points A and B is nothing but 4 times I2. So whatever is the voltage drop across these two is going to be your V open circuit or V Thevenin voltage. What is this I2? So in this case, I2 can simply be found out using the current division rule, right? So we can find out I2 using the current division rule. So using current division rule to find I2 makes things simpler, is going to be this 2 ohm impedance Z1, 2 ohms divided by 2 plus addition of these two, because the same I2 current is flowing through these two branches. We'll call this as one impedance, 4 plus J1. This is going to be 4 plus J1 times 4, or 4, this is nothing but 4 angle 0. Right, so this is times 4 angle 0. This is the current source. So this is my I2 value. Right? So we can solve this one. 6 plus j times 4 angle 0, which will come out to be take angle minus 9.46. So we calculated V Thevenin or V open source voltage. Now the second part is find out the Z Thevenin. So Z Thevenin can be found out. We need
to remove the sources. So remember, remove sources. Remove the sources. What are the sources in this circuit? We have the source as this current source, 4 angle 0. So we will open circuit this current source, and we can redraw the circuit as this open circuit path, only the impedances, 4 ohm, J1, and at this particular point, we will see what is the Z impedance. Now, this is nothing but a parallel combination of this 4 ohms and this J1 plus 2, right? So this is nothing but here inductor and resistor. This is 4, this is 2, and this is J1. And this is where we have to see Z Thevenin. Right? So Z Thevenin is going to be simply 1 over 2 plus J plus 1 over 4 inverse, which is going to be this value. Right? So now we know two values. We know V Thevenin, or V open circuit voltage. We know Z Thevenin. What is now the condition for the power to deliver maximum? The condition for the power, maximum power, is that ZL should be equal to the complex conjugate of Z Thevenin. So what is going to be ZL? It should be the complex conjugate of this number which we calculated. So the complex conjugate for this number is simply replacing the positive sign of J to the negative sign. And this is what we need to, this is what is our ZL. So we already found out what is asked for. Let's say if I have to find out what is the maximum power delivered to the load. So for all, this is just for your understanding. I will use a different color for you. So let's say I have to find out PL as well, maximum power. So maximum power is going to be, I can find it either using this formula, or I can also find it or using V open circuit square divided by R Thevenin. It's up to you, right? So let's say I'm using this formula. I can use both of them. For this one, I need to find out IM. So what is IM? IM is the peak value of the current. So what is IM? It is nothing but the load, IL. So how I can find out the load current? I can find out the load current using the open circuit voltage, right? So let's say I can redraw this circuit, V Thevenin, Z Thevenin, and this is ZL, which is the complex conjugate of Z Thevenin. And this is going to be my IL. So this is what I'm finding out right now. IL is going to be the V Thevenin divided by Z Thevenin plus ZL, which is Z Thevenin conjugate, right? So when I put these values, I already have these values of V Thevenin, Z Thevenin, ZL conjugate. Let me write it to avoid confusion, plus Z Thevenin conjugate. It is going to be 1.87 angle minus 9.5 degrees. So this is IL. I need to put this IL value to the power, and I can find out this PL by putting this value, which will turn out to be 2.47 volts. Right? So again, this is IM. I only need to put in this IM 1.87 here, because I need to put only the peak value, IM square. And RL is already 1.41. So this is what
how I can find out the maximum power which is delivered to the load for any kind of circuit given to us. Right? Okay. So I will now move on. So just to summarize it, again, this is how we find out the Z Thevenin. The Thevenin is nothing but a real part and an imaginary part. When the condition is that when ZL is equal to the complex conjugate of Z Thevenin, you deliver the maximum power, right? And this is nothing but PL is nothing but half of the open circuit square R Thevenin over 4R Thevenin squared, because RL is equal to R Thevenin. And it can be written, and we just derive this formula. Right? So finally, if this is the condition, and I already told you that you can also derive this using this expression. If you take the derivative with respect to the RL, you can actually derive this previous equation as well. All right, so now before we move forward, we need to understand what is the RMS value or the effective value. Right? So what is the R? This is a very important term because in often cases we need it's RMS and or the effective value is used interchangeably. However, we need to define an effective value for a periodic waveform. If we have a periodic waveform, right? The effective value is going to be the value of the current or voltage that delivers the same average power to a resistor as the periodic current. So I can write this as so effective power is for a periodic waveform can be written as power is equal to I square R, where I is the effective current. So again, the effective current, it measures the effectiveness of the current or voltage delivered to the load, right? So I effective square can also be written by power divided by resistor root square. What is this power? This is the average power we calculated in our previous lecture. Right? So P average, this is the average power. P average is nothing but I square, the square of the instantaneous power this is average power. When we put this value, when we put the average power value, sorry, in this equation, this is P. It is going to be, the R is going to be canceled out, and it is going to be 1 over T. We define the two instant of time, I squared instantaneous power times this one. This equation, this is nothing but it is actually the RMS value. This is the RMS value. And what is the RMS value? It is the root, we first find the square, we first find the square of the current, then we average it out and then take the square root of it. So this is how you find out the RMS value for this one. So this is nothing but RMS value. So I effective is the same as RMS value. So what is this IT? We can using I instantaneous current as a peak value of current minus theta. We put this one in this equation. We use the trigonometric identity for cos square of omega t, right? So using cos square omega t trigonometry identity, we can write I effective can be written as I m root 2, which is nothing but I RMS value. So we can similarly, we can show this for voltage as well. Exactly the same way we can show this for voltage as well, that V RMS is nothing but peak amplitude of the voltage by under root 2, which is V effective. Right? Okay. So if now we have an average value, right? We have an average value and we need to, if we have a power, we already know the power value. So if we have a power and we need to define this power, we derived this expression in our last lecture. So we have this average power, which is not dependent on time. So this average power can also be written in terms of its RMS value using these last two relations we just expressed. So we can write this one, and V RMS is equal to peak value divided by under 2. Here the peak value is there, so we will multiply it with root 2 and we will write RMS value. So this is nothing but under root 2 V RMS, and current is nothing but under root 2 I RMS, cos of theta V minus theta I. These under root 2 will become 2. This is going to be cancelled out with the denominator 2, and this term will be nothing but I RMS, V RMS, cos of difference of angle between voltage and current. So this is the average power in terms of the RMS voltage and current, which is normally used in industry. So now you can tell me that for a resistive load, if the load is a pure resistive load, what is going to be this P average in terms of RMS value? So for a pure resistive load, we know very well that current and voltage are in phase, so there is no difference between them. So in that case, the cos of 0 is going to be 1, and average value is RMS times power is going to be just the multiplication of voltage and current's RMS value. Or we can also write as RMS square over R times R, sorry, RMS squared times R. Or V RMS squared divided by R, right? However, for a pure reactive load, we know that this is either plus 90 degree or minus 90 degree. So when we put this in the above value, the power is going to be 0 for a pure reactive loads. So normally you will see the supply voltage is written, and this is used in as 120 RMS value, right? So this is the RMS values. Typically the supply voltage is written in terms of RMS value, 120 RMS. So if you need to convert that voltage to the peak value or VM can be written as the value times under root 2, which is equal to 70 approximately. So this is how we actually write the values for the effective value, the RMS value, and this is how we calculate them. Thank you very much.